Ever wondered if you could hop into a machine, press a button, and travel back to witness history or forward to see the future? It's a tantalizing thought, isn't it? The concept of time travel has always held a special place in our collective imagination. From H.G. Wells' The Time Machine to the cult classic Back to the Future trilogy, from countless sci-fi novels to mind-bending films, the idea of moving through time has fascinated us, stirred our curiosity, and sparked endless debates. But what if I told you that time travel isn't just a figment of creative minds? What if it's a very real, albeit theoretical possibility? Yes, you heard that right. While we may not have a physical, tangible machine that we can hop into and zip through time, the concept of a real-time machine is deeply rooted in one of the most profound theories in physics: Einstein's theory of relativity. Einstein's theory of relativity, in its simplest form, suggests that space and time are not separate entities, but are interwoven into a single continuum known as spacetime. Picture a trampoline. If you place a heavy ball in the middle, it creates a dent, a curvature. This is similar to how massive objects like stars and planets curve spacetime around them. Now, if you were to roll a smaller ball around the edge of this dent, it would spiral inward, just like how a planet orbits a star. This is the essence of gravity according to Einstein. Now, if spacetime can be curved, can it also be twisted and folded to create shortcuts? Could these shortcuts, or wormholes as they're called, be our ticket to time travel? So, a real-time machine isn't a contraption with buttons and levers, but a journey through the fabric of spacetime itself. This might sound far-fetched or straight out of a sci-fi movie, but remember, reality can often be stranger than fiction. And in the realm of theoretical physics, the line between reality and fantasy blurs, creating a world of endless possibilities. To grasp the concept of a time machine, we must first understand what we mean by space-time. Picture space-time as a giant, flexible sheet. Now, this isn't just a two-dimensional sheet, but a four-dimensional one, incorporating not just the three dimensions of space we're familiar with, length, width, and height, but also time. Imagine dropping a heavy ball onto this sheet. What happens? The ball causes the sheet to curve, to warp. This is similar to how mass and energy distort spacetime. The more massive or energetic something is, the greater the curvature it causes in the spacetime around it. This warping effect gives us what we commonly know as gravity. But how does this relate to time? Well, gravity doesn't just pull on space, it also pulls on time. And this is where things get really interesting. Gravity can slow down time. Yes, you heard it right. The stronger the gravitational pull, the slower time ticks. This phenomenon is known as time dilation. We see time dilation in action when we compare two clocks, one placed at sea level, where Earth's gravity is stronger, and the other at the top of a mountain, where it's slightly weaker. The clock at sea level, under stronger gravity, ticks slower than the one at the top of the mountain. This difference might be minuscule, but it's there, and it's real. And it's this principle that forms the basis of a real time machine. By creating an environment where gravity is incredibly intense, we could, in theory, slow down time to such an extent that a minute for us could equate to years outside that environment. In other words, the stronger the gravity, the slower time passes, which is the crux of creating a real time machine. Now, where does one find a powerful enough gravitational field to significantly warp time? The answer? Black holes and wormholes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape their grasp. Imagine a star, much larger than our sun, collapsing under its own weight. This intense collapse creates a point in space with insatiable hunger, consuming everything that ventures too close. That's a black hole for you. The immense gravitational pull of a black hole bends space and time around it. This warping of space-time is so extreme that it could theoretically twist time into loops, potentially allowing us to revisit the past or leap into the future. But there's a catch. Traveling into a black hole would likely be a one-way trip. The immense gravitational forces would stretch anything that enters into a long, thin strand, in a process whimsically known as spaghettification. Not exactly the most pleasant journey, is it? That's where wormholes come in. Wormholes, also rooted in Einstein's theory of relativity, are essentially shortcuts through space and time. If black holes are the insatiable monsters of the universe, then wormholes are the cosmic backdoors. They are tunnels connecting two different points in spacetime, potentially billions of light years apart. Here's the exciting part. Unlike black holes, a journey through a wormhole could theoretically be a round trip. Imagine stepping into a wormhole and emerging at a different point in space, or even a different time. The past, the future, distant galaxies, all could be just a wormhole away. However, it's crucial to remember that this is currently all theoretical. We haven't yet discovered a wormhole, and even if we did, it's uncertain whether they'd be stable enough to travel through. So, theoretically, if you could survive the trip, a wormhole could be your ticket to the past or the future. Time travel isn't without its problems and paradoxes, though. As intriguing as the concept is, it behooves us to grapple with several perplexing paradoxes that time travel gives birth to. For instance, the infamous grandfather paradox. Imagine, if you will, traveling back in time and accidentally causing the demise of your own grandfather. This would prevent your existence, and yet, here you are, an apparent contradiction. Then there is the mind-bending bootstrap paradox, a concept that challenges our perception of cause and effect. Imagine finding a book on time travel, using it to build a time machine, then going back in time to write and publish the very book you found. Who, then, is the original author of the book? These paradoxes seem to defy our understanding of logic and causality, making the concept of time travel even more enigmatic. Furthermore, time travel is complicated by the concept of the arrow of time. This arrow, in essence, points from the past to the future, indicating the direction of time's flow. It's why we remember yesterday but not tomorrow, why we grow older, not younger. This concept arises from the second law of thermodynamics, which states that entropy, or disorder, in an isolated system always increases with time. If time travel were possible, it would require reversing this arrow, essentially decreasing entropy, which contradicts our current understanding of physics. This doesn't necessarily rule out time travel, but it does suggest that we would need to rethink some of our fundamental assumptions about the nature of time and the universe. These paradoxes remind us that time travel, while fascinating, brings with it a host of mind-boggling challenges. As we continue to explore the possibilities, we must also strive to untangle these paradoxes and deepen our understanding of this intriguing concept. After all, the journey to understanding time travel is, in many ways, a journey into the unknown, a journey that continues to captivate our collective curiosity. So what does a real time machine look like? It's not a machine at all, but a journey into the unknown. A journey that beckons us to traverse the intricate tapestry of space and time. A journey that, while seemingly fantastical, is rooted in the bedrock of scientific theory. Earlier, we delved into the concept of space-time, that four-dimensional fabric of the universe, where time is but a passenger aboard the ship of space. We explored how gravity, that invisible hand guiding celestial bodies across the universe, warps and bends this fabric, creating phenomena like black holes, these cosmic whirlpools where space-time plunges into oblivion. We spoke of wormholes, those theoretical shortcuts through space-time, offering a tantalizing hint at the possibility of time travel. If space-time is an ocean, then wormholes are the hidden currents beneath the surface, shortcuts that could potentially allow us to outpace the relentless march of time itself. But what does all this mean for our time machine? Well, if such a thing exists, it's not going to be a DeLorean or a phone booth. It's not going to be a contraption of gears and dials, but something far more profound. It's going to be an understanding, a mastery of the laws that govern the universe. While we don't have the technology or understanding to create a time machine yet, the theoretical foundations exist. Theoretical physicists and cosmologists are already laying down the groundwork, exploring the very boundaries of our understanding. As we stand on the precipice of this vast unknown, we can't help but feel a sense of awe and wonder. The cosmos, in all its grandeur, is a puzzle, and we are the curious minds trying to piece it together. So next time you daydream about visiting the dinosaurs or seeing the future, remember, your time machine is out there somewhere in the vast cosmos waiting for you to uncover its secrets.